looking. Good day, everyone. We'll be looking at display method of analysis, which is moment distribution method. And in this method, it was discovered by Adi Cross in 1930, and it's an analysis method that is very, let me say, easy to approach once the principle is understood. Now, let us take, for instance, we have a beam, a uniformly distributed load beam from A to B, and this is the uniformly distributed load W, and this is a point load P acting at the center here. Now, in this beam, there will be moments at the end. We have moments at AB and likewise moments at BA. That is moment from B towards A, and this one moment from A towards B. Now, looking at it grammatically, this is what we have. Let's say this is a fixed beam. Because it is in a fixed beam, we have moment at the support. Now, imagine it's being loaded at with 800 Newton force at the centroid, as shown here. The first thing we're going to do when we're treating moment distribution method is that we have to have our sign convention. Now, this sign convention, it helps us to be able to know, okay, this is the direction I want to follow. Now, for moment distribution method, we are assuming that clockwise moment that acts on the member are positive. That is, when we are considering moment in this direction, they are positive. So once this is noted, then we'll proceed to the next agenda, which are fixed end moments. Now, every beam or every beam arrangement has their own fixed end moment, and there are different fixed end moments for each particular for each particular beam detailing or beam support type. For instance, now when we have a fixed end moment like this one, the fixed let's say when we have a beam like this, the fixed end moment, the formula we'll be using is WL over 8, where W or P is the point load and L is the span, and then over 8, that 8 is a constant for this type of loading. However, when we have a loading like this, we are not going to use that. There's another formula for this kind of loading. When we have a loading like this, there's another formula for that. So depending on what we are having, and even when we have a loading of this sort, maybe something is not uniformly the load is not acting at the centroid, there's another fixed end moment for that. There's a fixed end moment table that we'll be using. I will try and show us how this fixed end moment table looks like. Now, before I proceed, let me just show us our fixed end moment table, and then we proceed. Sorry, I will send the fixed end moment table after to the class. Now, let us look at now we have talked about fixed end moments and how it's being calculated. We said it's PL over 8, where P is this point load and L is this span from here to here. So to calculate the fixed end moment for this, it will be P, which is 800, times L. The whole L is 10. Not that you consider 5 meter, no, the whole full span is the L. So P times L all over 8, which is 800 times 10 divided by 8, which is giving us 1000 Newton meter. Now, let's consider there's something we call the member stiffness factor. The member stiffness factor, the way we treat it is like we consider a beam. Let me move to that beam. We consider a beam as shown here. We consider this beam as shown here, and in this beam, we believe that it is pinned at one end and it is fixed at other end. So when it is pinned at this end and it is fixed at this other end, there will be a rotation at this particular end here. There will be rotation at this end, and once there's rotation, because it is pinned and it is not fixed, there will be a displacement. Imagine this particular object being turned in this direction. There will be a displacement in this format here. Now, After this displacement, there will be an angle of rotation formed here. This angle of rotation, it has effect on our fixed end moment, on our stiffness, because if it is fixed, there won't be any theta here, because as you can see, because of this rigidity here, there's no rotation at this other end here, but there's a rotation at this end. Now the moment due to this rotation is given by this formula, 4 EI over L theta A, and the far end fixed is 4 EI over L because there's no rotation, so the far end fixed is 4 EI over L. This particular K value is known as the stiffness factor, and it is defined as the amount of moment that is required to rotate this end A at let me say at 1 radian, that is to make it to rotate to 1 radian. That's the stiffness factor here. And as you can see, the notice here, it said the stiffness factor at A can be defined as the amount of moment required to rotate the end A of the beam at 1 radian. So let's proceed to the next point. Now there is something we call joint stiffness factor. Now let us say, for instance, we have a beam that is fixed in this format. We have it fixed here, and fixed here. Now you know this, let's say this point A, and this point D, this point B, this point C. Now there's the way we consider this kind of beam, we each of the members, they have their own stiffness. Let's say member AB, they have their own stiffness. Member AC has its own stiffness. Member AD has its own stiffness. Now imagine we have this kind of member. Now how do we calculate the total stiffness of this member? Let's say the total stiffness will be summation of the stiffness of this one plus the stiffness of this plus the stiffness of this. Now it says joint stiffness factor. If several members are fixed connected to a joint, and each of their connected to a joint, and each of their far end is fixed, then by the principle of superposition, the total stiffness factor at the joint is the summation of the stiffness factor at the joint, that is KT equals the summation of K. What it means is that, imagine this one is having KAD of 1000, this one is KAD of 400, and this one is KAC of A to C of 5000. So the total stiffness at this joint is summation of this plus this plus this, which is equal to 1000 plus 4000 plus 5000, which is 10,000. Now that is the joint stiffness factor. Now this value represents the amount of moment that is needed to rotate this joint at an angle of 1 radian. That is to make it to rotate at an angle of 1 radian. Now after considering this, the next thing we will be going into is our distribution factor. If a moment M is applied to a fixed joint, the members with each supply a portion of the resisting moment necessary to satisfy the moment equilibrium at the joint. That is to say, each of the member, they will be supplying a moment, and they will be trying, as this one is, maybe this one is turning this way, this one will try and balance it like that. As you can see here, this one is turning this way, this one is turning this way, this one is turning this way, and there should be a counter moment to balance it. Now how do we what is this distribution factor? It is that fraction of the total resisting moment supplied by the members. That is the total fraction of the fraction of the total resisting moment that is supplied by the member is the distribution factor. So how do we obtain this distribution factor? It is very easy. All we just need to do is we assume that an applied moment M causes the rotation at an angle, the joint to rotate at an angle theta, and each member rotate by this amount I. Now, if the stiffness factor of this ith member is Ki, then the moment contributed by the member is Mi equals to Ki theta. Note this, Mi equals to Ki theta. And the other time we know our Ki to be equals to what? Ki is equal to, okay, I will still go into that. I think the other time we said Ki is equal to 4ei over L. So that's what we are actually going to be using. So now, looking at the distribution factor, this distribution factor is Mi over M. What it means is that the Ki of this member we are considering over the solution of all the Ki that is existing there. That is, if we have a moment for the moment M having two member M1 plus Mn, the distribution factor is Ki of theta plus Kn of theta, which is solution of Ki. Now, at the end of the day, we are going to have this, because that theta will cancel each other, then we only have K over summation of K. What it means is that if we want to calculate the distribution factor for this particular member AD now, it will be the stiffness of KAD all over the summation of this one, stiffness of this plus stiffness of this plus the stiffness of this. So let us look at it as under this calculation. We want to calculate the stiffness factor of AB. We say AB is 4,000. KAB is 4,000. Now, what's the distribution factor for KAB? It will be this one all over the total summation of this one plus this 2 plus this 3, which is 10,000. So at the end of the day, we have 0.4. So likewise, if you want to consider for Ka to C, the one, because we are considering Ka to C, and the similar for A to C, the one member we'll be using is Ka of C, and then that will be 5,000 divided by 10,000. And likewise, if we are considering A to D, it will be 1,000 divided by 10,000. I believe that is clear enough. So let's go to the next point. So having arrived at this distribution factor, our moment that at the joint, let's say if our moment is, let's say 2,000 Newton meter, let's say that's the total joint moment acting at this particular place. Now each of the members, the moment acting on each member can be regarded as, let's say the moment will be 2,000 times whatever their distribution factor is. For instance, for this one we have it as 0.4. so its own distribution factor, its own moment for A to B, moment towards A to B, that is from A towards B, the moment acting is 2,000 times 0.4. That distribution factor is like is taking a fraction of what moment each of them would take from the whole total moment. So likewise, the one for A to C is going to take 0.5 times the total, let's say 2,000 Newton meter. So 0.5 of this, that's 1,000 Newton meter. That's what A to C is going to take. And likewise, A to D, the same thing applicable. It's going to take 0.1 times 2,000. Total moment is 2,000. So what you are trying to say is that if the total moment acting here is maybe 5,000, whatever it is, this helps us to know what moment each of the member will be having or will be taking in the total amount of moment being displaced there. Now the next thing we go to is the member's relative stiffness factor. Now in this member's relative stiffness factor, what we're trying to say is that, let's say a beam is made up of the same material. Now the stiffness factor for this particular member will be, instead as against the when it is having the same when it is having the same material composition, the
the the stiffness factor, relative stiffness factor will be I over L. What it means is that because it's the same it's the same material, there's no the theta A or whatever it is will cancel each other. The common factors will cancel each other, and we'll be left with just I over L, because that's for the relative stiffness factor, for the far end fixed rather. Now, what do I mean by far end fixed? I'm talking about this far end that is fixed. That's far end fixed. Unlike the illustration we did the other time, where we have this particular end. This end is the far end fixed. So let me proceed to what I'm doing now. So there's something we call carryover factor. Now, this carryover factor, the way I will explain is that in moment distribution method, we try to carry the after getting our distribution factor, applying it with moment, there's moment that will be transferred to the other end or to the support, and we'll try to balance them. So we'll try to take it to the other end, that's carryover factor. And the way we do the calculation for this is very simple. I will explain. For instance, we are considering this beam here, and we said that moment at A to B is 4EI over L theta A, as we explained the other time, and the moment about this side is 2EI over L theta A, because there's no because this side is fixed, unlike this side where we are 4EI. So if you look at the two, this side is 4EI, this side is 2EI over L. What is the difference between the two? The difference is just this one is just twice of what we have here. So that is, this one is twice of what we have here. So in other words, the moment about this point is half of what we have here. This one is 2 times higher than this, so this one is just half of what we have here. So in other words, the moment M at the pin induces a moment of M prime of half of M at the wall. The carryover factor represents this fraction of M that is carried over from the pin to the wall. Hence, in this case of a beam with far end fixed, the carryover factor is just half. Now, the plus sign indicates both moments act in the same direction. Now let us let's proceed to the next point. Now we want to look at moment distribution factor for beam. Now, the other time we said we have talked about the sign convention. Then we are going to calculate. Let's look at this beam that we have here. It is very easy for us to do the calculation, though I'm using IB per feet, but that doesn't mean, even if it is native per millimeter, you can always equate it. Now imagine this beam here. We have this beam spanning from A to C and having a support at B, a pin support at B. Now this side is fixed, this side is fixed, but this side is not fixed. Now the first thing we are going to calculate is the stiffness factor. The stiffness factor. Now this stiffness factor, I told you that is K equals to 4EI over L. Now the same formula is what we are applying here. Now the stiffness factor on either side of B, that is at this side and at this side, are this is B to A and this is B to C. So for B to A, it is 4E times I. What is the I? The I is given here. This is the I here. Now what it means is that when we have different I for members like this, that means the material for this section for this side of the beam differ from the material for this side. So that is why we have to take into consideration this the stiffness of that particular, and let me see, the I, the moment of inertia of that particular material. Now the second moment of area rather. Now by the time we do our substitution, 4e times 300 divided by 15, we have this. Now the same thing applicable for B to C. K of B to C, it is 4e times the I is 600 inch raised to power 4 and the span is 20. Please note that this L, it differs because this one is 15, this one is 20. You can see from the calculation we have 15 here and we have 20 here. So we have to consider the span for each of the member we are considering. So now the distribution factor, as we all know, the distribution factor, as we all know, is K all over summation of K. What do I mean? If I'm considering this one, let's say this is my K all over summation of this plus this. And if I consider this one, this member, it will be this all over this plus this. So the distribution factor is equal to the stiffness K of the member we are considering all over the total summation of K for that particular joint. Now we have it as K of AB or BA is this, which is this divided by summation of this plus this. That's what you can see here. This all over summation of this plus this, and we have it as 0.4. Likewise, when we are considering the distribution factor for B to C, that is B to C. What's the K of B to C? We have it as B to C is 4U 30 inch raised to power 4 per feet, and that's what we're having as the numerator here all over the total summation here. At the end of the day, if you sum these two together, they should give us 1. So that's the distribution factor for this particular member. So at the walls, that is at joint A and at joint C, the distribution factor depends on the member stiffness factor and the stiffness factor of the wall. Since in theory it will take an infinite size of movement to rotate the wall, because there is no as I explained the other time, at the fixed end there's no rotation that is being considered there. Now the distribution factor at that particular end, at particular end A or at particular end C, because it's fixed, is 0, and this is the calculation for that. So let me proceed to the next point. Having arrived at all this fixed end and distribution factor, knowing all those calculations, the next thing we will do is that we go straight to our computational table. Let me see. So the fixed moment table, it looks like this. I don't know whether you can see this. Let me just put this way first. Okay, it looks like this. And what it means is that, let us consider this as a beam. We believe all the ends are fixed, so the fixed end moment for when we have this kind of loading condition where our P is at the center is PL over 8, and likewise for fixed end moment for B2 is PL over 8. Now when it is not loaded at the center, when we have distance A that differs from distance B, the fixed end moment is PB square A over L square, while this other side will be PA square B over L square. Now imagine it is being loaded in this format, that we're having 3 different points. This one is loaded at one third like that. The fixed end moment is 2PL over 9 and 2PL over 9 for this particular case. Likewise, the same way we have, if it is uniformly distributed load like this, we have it as WS square over 12 and WS square over 12 at this side. Now if we have it as in this condition, let's say from span A to B, please, it's span A to B now, and half of the span is uniformly distributed load. This is the formula: 11 WS square over 192, while this side will be 5 WS square over 192. I will get us a clearer one as we proceed. So for this particular scenario now, we have fixed air moment for WS square over 12 equal to ws square over 12. Now what we try to do is that if we are considering fixed air moment, let's say I'm starting from here, B to C. If I consider this side as negative, I consider the other end as positive. That is, if I'm considering this fixed air moment from B to C to be negative, then fixed air moment for C to B will be positive. Now, which is exactly what we have here. You can see W minus WS square over 12. We got minus 240. This is the 240. This is the uniformly distributed loop. Now, L is the distance and the span, 20 over 12, which is this. Now, if I'm considering the fixed air moment from C to B, C to B, that is in this direction. Sorry, let me put my pen. From C towards B, the fixed air moment is WL square over 12, which is 240, which is this, divided by times 20 square. 20 square is the span from here to here, divided by 12. Now, so you can see from here we have WS square over 12, which is what we are using. So depending on what, but don't forget, if we are considering this side to be and the left hand side to be negative, its right hand side will be positive for every span we are considering. So let me proceed and just put this one away. So the next thing we're going to do is we draw our table based on the information we already have. Now the way we draw the table, we have joint A, joint B, joint C. Now what we are going to do is that we first put our joint A, B and C. Now for each joint we have what we call the members. For instance, for this one we have member A to B, we have member B to A, we have member B to C, and we also have member C to B. So we write our member from under A. How many member we have under A? We have A to B, A towards B. Now under B, how many members we have? We have B going towards A and B going towards C. That we have BA and BC. Now under C, we only have member C towards B. Now after putting our CB down, then we are now going to write our distribution factor, which is what we calculated the other time. Let me remove this. So now the distribution factor as calculated for members A to B is 0. We put the value. For members C to D is 0. We put the value. But for members B to A is 0.4 and B to C is 0.6. We put those values down. Then we will now put we'll go to the next point, though I think I will make a clearer table so that we'll be able to understand based on this fixed air moment. Now the fixed air moment calculated for each of them, we have it for B to C and C to B. We have minus 8,000 for B to C, B to C minus 8,000, and C to B is 8,000. So we put it down in this form. Now the next thing we are going to do is we apply the table, we multiply our distribution factor with our moments that we got. Let me use this to explain one by other. So we begin by assuming joint B is fixed or locked. Then the fixed air moment at B then holds span BC in this fixed or locked position as shown in figure of this. This of course does not represent the actual equilibrium situation, yes, but what I'm trying to where I'm trying to arrive at is to correct this. He said, since the moment on each side of the beam must be equal but opposite, to correct this, we apply an equal but opposite moment of 8,000 IB feet to the joint and allow the joint to rotate freely as shown in this diagram here. As a result, a portion of the moment are distributed to the span BC and a portion is distributed to span BA in accordance to our distribution factor or our stiffness that we have calculated. Now, the moment at BA is 0.4 times this 8,000, while the moment at BC is 0.6 times 8,000. So we have this one to be 3,200 here, and we have BA is 3,200, and this side is 4,800 out of the total moment acting on this particular point. So what we're trying to say is that, let's say this is the fixed end moment. If half of this from this one, we said BA is taken from this, just like the example we did the other time, that from this example that we said out of the total moment of 2000 Newton, this end is taking 200, this side is taking 800, this side is taking 1000. The same thing we are trying to apply in this scenario. We are trying to say out of this total 8000 IB feet, that what is going towards BA, what is going towards BC. So from this calculation, we realize that 3200 is going towards this side of BA, and 4800 is going towards BC. So what we just do is put the 3200 for BA and the 4800 towards BC. Now, having done that, I told you the last time, I will first put our normal calculated fixed end moment, which is minus 8,000 and 8,000. Now, in this table here, we have realized that, okay, this side is taking 3,200, this side is taking 4,800 out of the total 8,000. So what we now did is that in this formula, in this particular instance the other time, we told us that when we have a fixed moment here like this, and we have a rotation here, that the moment here is twice of what we have here. That is, this side is half of what we have here, as explained. Now, the same principle is what we want to apply for this particular scenario here. Half of this particular moment that is on BA, we are transferring it to AB, and half of what we have at this BC, we are transferring it to CB. That is, half of what is happening here, we are transferring to this side. Half of what is happening here, we are transferring to this side. Please note, we are not transferring from the fixed to the from the end. We are not transferring to the center. Well, we are transferring from this joint here to the end. Having done that, we transfer 3,200. Half of it is 1,600, which we have here, and half of 4,800 is 2,400. At the end of the day, we will now sum all the moments together, and then we have summation of moment. From here, the summation is just 1,600 we put here. Summation of this is just 3,200. Summation of the one for here is just minus 8,000 times 4,800. That's minus 3,200. Summation of this plus this is just 10,400. So this is the moment acting at AB. This is the one acting at BA. This is the moment acting at BC, and likewise at CD. So that is just the way the calculation is being done for this. So let me just see if there's a little explanation that is written in the note that I can see add to it. It says this example indicates the basic tenderness when distributing moment at a joint. We determine the unbalanced moment acting at the initially locked joint. We unlock the joint and apply an equal but opposite unbalanced moment to correct the equilibrium. Then we distribute the moment among the connecting span and carry the moment in each span over to its other end. These tests are usually presented in tabular form as indicated here. And here the notation this DISTCO is called indicates a line where moments are distributed then carried over. In this particular case, only one cycle of moment distribution is necessary, since the wall supports at A and C absorb the moment and no other joints have to be balanced or unlocked to satisfy the joint equilibrium. Once distributed and once done, we said no further joints have to be balanced to or unlocked to satisfy the joint equilibrium. Now, what we're trying to say is that if we have like A to B, B to C, C to D, then we'll be transferring from B towards A, and likewise C2, because joint C2 will be transferring to B and is also transferring to D.
but because this case is just ABC, where C is the fixed end, it's not support, it's not the support, it's just it's not this, it's not don't let me say it's a support, but it's not a fixed support. And this side is a fixed support here, but if it's not a fixed support, if it's a, let me say, a simply supported as we have here, and we all now have midpoints D as the fixed support, then we'll transfer from C to B like that. Now the scenario is that if we break out what is happening here, this is what is going to happen. We have the moment of 1600 here, we have 3200 here, we have we have BA 2200, we have minus 3200 at this other end, and we also have 10,400 at this other end. Now the moment, you can see this is the moment, this is the moment here, this is the moment here, this is the moment here. And if you look at the sign convention, you will see that what we have here, I explained the other time that when we make a cut on a beam or a member, that the sign changes. That is, if it's going upward here at this side, it is going to be coming downward. So or the rotation will change at this other end. Not that will make it to be, this one is coming clockwise here, but here is coming anti-clockwise. That's what I'm trying to explain here. So let me proceed. So let's proceed to the, I believe everybody can calculate the shear force from the shear force is very easy to calculate. I don't think I should be explaining that for us. Now this is another example here. Now you can see the other distribution factor and the fixed element are the same as computed previously. They are listed on line 1 and 2 on the table now, and then we begin by unlocking the joint C and placing an equilibrating moment of minus 8,000 feet at the joint. So what we're trying to say is that, just like we have at the other time, putting now our values, 8,000 fixed moment, 8,000 minus 8,000 and 8,000 here, the same thing applicable to the next one, minus 8,000 and 8,000 here, as we have as in point 2 here. Now in this particular scenario here, this is another method they are trying to explain to us. Now it says we begin by unlocking the joint C and placing an equilibrating moment of minus 8,000 at the joint. The entire moment is distributed in member CB. Since 1 times minus 8,000 is equals to minus 8,000 this, then the arrow on line 3 indicates that half of minus 8,000 IB feet is equal to minus 4,000 feet is carried over to joint B, since joint C has been allowed to rotate freely. Joint C is now relocked. Now what is this trying to say is that we take half of what we have here. Firstly, we multiply this one times this, then times, let me say, this times negative of this, that's minus 8,000. Then we now take half of what we have here, we transfer it to this side, which is minus 4,000. That's exactly what they are trying to explain here, that the arrow on line C indicates that half of minus 8,000 IB feet is equal to minus 4,000 is carried to joint B. Since joint C has been allowed to rotate freely, joint C is now relocked. Since the total moment is balanced, a line is placed under the minus 8,000 feet moment. We will now carry the unbalanced minus 12,000 feet moment at joint B. If you add this plus this, that's minus 12,000 that they're talking about. Now we'll now carry it, and we distribute it to BA and BC. What I'm trying to say is that this summation of this and this is 12,000, right? Minus 12,000. Now we will not distribute it to this joint and this joint. And how are we going to distribute it? This minus 12,000 that we sum here, we multiply with this minus 12,000 times 0.4 will give us 4,800. Then minus 12,000 times minus 0.6 will give us 7,200. So if you add this plus this, that's 7,200 plus 4,800, it will give us the same 12,000, that is this total 8,000 and 4,000. The only difference you can see is that because we are multiplying with negative of this, we have, if this one is a negative, we will have this one as positive. And then after that again, it says the okay, it's just the same explanation is what is written here. 0.4 times this is 4,800, and then 0.6 times 12,000 is 7,200. Is on line 4. Now, also note, plus half of that moment must be carried to the fixed wall A and roller C. That is, what we are going to say is that what we have here, half of it will be taken to this point C, half of it will be taken to this point A. So for this one now, we have 2,400, half of 4,800 will be 2,400, and half of this is 3,600. So we have that there. Then we now proceed again. It says, let me underlining them so that when I'm explaining back, we first said this line 3. Okay, half of this movement must be carried over to the fixed wall A and roller C, since joint B has rotated. Now, and again, joint C is unlocked, and the unbalanced moment at roller C is as done previously. The results are now on line 5. Now, this line 5, what did they do in this line 5? You say here, this one times negative of this, we have minus 3,600. This one times negative of this, we have minus 1,800. Or let's do the calculation. Let me just punch out my calculator out so that I do it. So we said we have transferred half to this side, half to this side, and half to this side. So we want to, how do we arrive at this one? For this one now, we sum this plus this plus this, we have minus 1,800. So let me bring out my calculator. Where are you? Over here. So sorry. We said we are after arriving at this, which we explained, this times 12,000 times 0.6, we have 7,200 for this side and 4,800 to this side, and then half is distributed to this side, which is 3,600. Now the next stage, which is this, is what we, how do we arrive at this? From this side, the same way we did here, that what we did in point 3, taking half to this side, we took half of this to this side. That's half of 3,600 will give us 1,800, which is what we have here. Now after I arrive at this, what are we going to do? We now multiply this, multiply this by 0.6 for this one, and this one, that is this times minus 0.6 for this, and this times minus 0.4 for this side. So if we do that our calculation, I don't know why my calculator is not showing on the screen of recording, but that's 1,800 times 0.6, it will give us 1,080, which is this. And then if you say 1,800 again times 0.4, it will give us 720, which is this.
So having arrived at this, the same thing we did here the other time. We take half of this to this side and half of this to this side. Half of 50 80 will be 540, which is what we have here. Let me erase that. Half of 1080 is 540 and half of 720 is 360 we have here. So having done that, we take this one down again, which is minus of this, and then we take half to this side again, which is minus 270. Then we multiply again by 0.6 by 0.4 negative of this, we have 108 162. Then we take half to this side, take half to this side, then this half negative of this comes here. Then having half of it coming here, we take half to this side again, which is 40.5. We multiply 40.5 by this, multiply 40.5 by this, we have the result here, where we take half to this side, take half to this side, then half, and this one times negative of this comes here down here again. We now take half to this side again. That this multiplied by this will give us this multiplied by negative of this will give us this. Then we take half to this side and half to this side again. So we have 1.8, then multiplied by negative of this will give us this. Then we take half of what we have here, take it to this side, which is minus 0.9. Then this minus 0.9, we multiply it with minus 0.6 for this and minus 0.4 for this side. So we have this. Now what we continue this kind of process until we have something very close to zero, and something very close to zero, then we stop. Then at the end of the day, we will now sum every of the fixed end moment together and get the value. The value we arrive at is the sum fixed end moment for each of those particular joints we are considering. So that's just the second method that is being illustrated here. If there's any question on that, you can always ask me at the comment section, or you can always send your question to my WhatsApp page for further clarification. So we should try as much as possible. We should try and do other calculation. I want us to practice this particular example, practice it, and then whatever is not clear enough on this particular example, kindly let me know on the comment section or ask your question. But please, before you ask question, make sure that you have done the calculation. You have your calculation sheet, that is, you have your calculation written out, and to the extent of where you are having problem, then where you are having problem, you highlight it, you underline the area for me, so that I will be able to explain for you easily. Because if you don't put the calculation, you can't expect me to be going to the textbook to make explanation on that. So to make it easier for me, just do that for me. And if there's any question, kindly let me know. So I'll be dropping. Don't forget, this one is just for the calculation, so you complete it to the end and then you submit it to me. That is, you complete the table, distribute it to the respective places, then you can submit to me. Any question? So see you in my next class.